This is part 1 of my summary of the Deep Learning book, authored by those presented on screen here. At times I will quote the book directly and use images from the book. Thanks for the authors for granting me permission to do so. I'd encourage any first-time viewers to watch my video explaining the motivation and intent of this project before diving in if you haven't already. This chapter is more informational than technical, introducing the reader to the key ideas and history of machine learning. So we'll see how it goes, and I'll develop my presentation style in the future most likely and try and improve it along the way throughout this project. So the concept of AI isn't new, but we've only been able to try and implement it in more recent decades. Quote, "The true challenge to artificial intelligence proved to be solving the tasks that are easy for people to perform, but hard for people to describe formally. Problems that we solve intuitively, that feel automatic, like recognizing spoken words or faces in images." End quote. Solving these problems is the topic of the book. How to do so? Quote, "Allow computers to learn from experience and understand the world in terms of a hierarchy of concepts." End quote. And allow a machine to learn from scratch and work up the hierarchy. It's called deep learning because complex tasks require many simpler concepts, i.e. many layers, creating a deeper system. Early successes occurred in sterile environments. For example, chess strategies can be complex, but the rules describing the world of chess aren't. It's a relatively short list compared to the rules describing the real natural world. Computers can't yet do innumerable things humans do regularly, such as construct cohesive arguments, because so much circumstantial knowledge about the world goes into nearly every action we make. Quote, "One of the key challenges in artificial intelligence is how to get this informal knowledge into a computer." End quote. The knowledge-based approach to AI attempts to solve problems by hard coding in knowledge statements about the world, from which the system can then make inferences. In short, these have proven ineffective and unwieldy. After all, can you imagine trying to type in everything you know, every fact that exists about the world? So it's not hard to understand how those strategies haven't proven very effective. AI systems need the ability to acquire their own knowledge by extracting patterns from raw data. This capability is known as machine learning. End quote. This allows machines to make decisions that appear subjective. Simple machine learning algorithms make decisions based on the data they're given, so it's critical that the data be good. The degree to which data is representative is one measure of data quality. The classic saying is garbage in, garbage out. Results will not be good without representative data. Representation can also encompass the medium by which the data is inputted. For example, you can imagine that arithmetic with Roman numerals would be much harder for you to do than with Arabic numerals. So if arithmetic is the algorithm you're running, and then the type of numeral can be considered as the medium, the data medium that's the input is being represented as. So you can see how that would make a big difference. Machine learning problems regarding identification of entities, whether from audio, video, or another medium, demand that the person designing the program effectively define the features that are to be extracted. For example, you wouldn't determine where a car lies in an image purely based on the color of single pixels in isolation, as cars come in different colors. Cars have wheels, so that could be a good feature to choose to look for. But the question is then, how does one train a computer to recognize what a wheel is? Consider these photos, and try thinking like a computer. Given the lighting, the shape of the wheels, the shadows, angles of view, etc., there can be tremendous disparity between the examples of wheels at the resolution of pixels. Representation learning is the approach where machine learning is used to identify the representation as well as the mapping from representation to output. Learned representations often result in much better performance. End quote. So this quote I just read describes how you might start from a slate like this, where you have the objects on the left and the objects on the right are defined by the programmer. So if you could somehow robustly define these entities on the left, like fur, eyes, wings, then in theory an algorithm could learn to map these successfully, images containing these, onto the objects to identify those objects, such as bird, mammal, whatever the case may be. So, as that quote just mentioned, the idea is that these algorithms actually learn to be much more effective when they learn not only the mapping, the arrows, but also the representations themselves. As mentioned earlier, feature design is critical. Usually that is done by identifying the distinct factors of differentiation. So, in a function like this, if you consider the identification of an object by an algorithm as a function, then these variables, a, b, c, etc., x, y, z, are the factors of differentiation. These are the unique characteristics that could describe an entity, and when considered together, explain the various ways in which one data sample might differ from the other data samples. For example, imagine trying to teach a computer to understand speech in a given language, using many samples of various people speaking. While all those data samples are alike in that they are speech samples, they have a number of factors of differentiation, such as the speaker's age, sex, accent, emotion, and the particular words they are speaking. These different factors lead to each sample having practically no similarity to other samples when considered at the very granular resolution of the audio data, even though the samples are alike in the abstract representation of them being audio recording of speech. Factors of differentiation can be qualitative or quantitative. One barrier to the application of machine learning techniques is the fact that such a wide variety of differentiating factors can all be at play and impact all data samples in different and unique ways. Deep learning makes representation learning in these complex or convoluted scenarios possible by using many layers of interpretation to build up complex representations, such as recognizing what a person is from simpler representations, such as specific combinations of contours and other features. And contours, in turn, a simpler representation, can be further identified by simpler representations as specific configurations of lines and edges. The canonical example of this kind of method is the multi-layer perceptron. The layers beyond the initial layer are called hidden because they consider abstractions generated by the earlier layers, originally based on the content of the image. Since these abstractions exist within the representation, they're typically not the final product, and so they're not immediately accessible to us. What we see is the output from the final layer, but what the intermediate hidden layers see is not the image itself, but what the prior layers pass on for computation. An alternate view of this model is that instead of using layers to learn what the right representation is for classification, that instead layers facilitate the computer learning and multi-step computer program. With this mental model, you can consider this, quote, each layer of the representation can be thought of as the state of the computer's memory after executing another set of instructions in parallel, end quote. More layers in the network would then correspond to more instructions in the sequential program. In this way, not every single layer deals exclusively with the factors of variation or differentiation that explain the input. For example, the existence of a single edge doesn't necessarily relate to one of the factors of differentiation mentioned earlier. For example, if an edge is identified in an image of the car, that won't help in understanding the angle of the sunlight hitting the car, which is one factor of differentiation. But the representation of that edge can be used to build a more abstract representation, which brings us closer to the final output, such as perhaps considering that edge as a part of the fender. The depth of an algorithm can be measured in two ways that are presented here. First, quote, the length of the longest path through a flowchart describing how to compute the model's outputs given its inputs, end quote. So if you imagine a flowchart that is talking about steps of computations, adding, multiplying, etc., that flowchart, the depth of it, or alternatively, the depth of a model can be considered as, quote, the depth of the graph describing how concepts are related to one another, end quote. So since many computations can go into the development or defining of a conceptual object, the computation graph is usually much deeper than the concept graph. According to the text, there is not currently a standard way to answer the question, how deep is a deep model? But either of these methods might be used. Quote, "To summarize deep learning, the subject of this book is an approach to AI. Specifically, it is a type of machine learning, a technique that enables computer systems to improve with experience and data. We contend that machine learning is the only viable approach to building AI systems that can operate in complicated real-world environments. Deep learning is a particular kind of machine learning that achieves great power and flexibility by representing the world as a nested hierarchy of concepts, with each concept defined in relation to simpler concepts, and more abstract representations computed in terms of less abstract ones." End quote from page 12. So this diagram shows the relationship or the nesting in the different kinds of learning techniques that have been developed. And you can just pause here if you want to take a look at this. It's a flowchart describing how each of those techniques function in very simple terms. The next section is titled "Who Should Read This Book?", from which I'll share some details for the benefit of viewers who might follow along. The authors specify two targets: undergrad or graduate university students learning about machine learning, and software engineers who do not have a machine learning or statistical background. I think I fall into that camp, so hopefully you do too as the viewer. The following are the author's descriptions of the sections of the book, which I'm just sharing as an FYI. My intent is to work through the entire book, but I feel, or at least all the parts that I feel are relevant to my interests or background. The authors state that those who just want to implement a working system need not read beyond part 2. Note that the following assumptions are those that the authors make about the reader: that the reader is familiar with programming, has a basic understanding of computational performance issues, complexity theory, introductory level calculus, and some of the terminology of graph theory. I think I have these bases mostly covered, except perhaps for complexity theory. When I encounter a part of the book I can't make sense of with my prior knowledge, I'll do some outside research and share what I find in these videos, so a viewer coming at it with the same knowledge as I have would be able to follow along. The trends in the history of deep learning are presented as follows. Deep learning has had a long and rich history that has gone by many names, reflecting different philosophical viewpoints, and has waxed and waned in popularity. Deep learning has become more useful as the amount of available training data has increased. Deep learning models have grown in size over time as computer infrastructure, both hardware and software, for deep learning has improved. And lastly, deep learning has solved increasingly complicated applications with increasing accuracy over time. While it might be a novel concept in the public consciousness, deep learning dates back to the 40s. It only took on this latest name, deep learning, in recent years. The field has been rebranded many times based on shifting perspectives in the community of practitioners and researchers. This chart shows the different trends in the prominence of some of the theory's names over time. The third wave is stated to be too recent to appear in this chart based on the data source from Google Books. You can refer to the textbook for more sources and information, such as examples of what work was done in each of these periods, which is pretty interesting. That's on page 13. The term artificial neural networks is used as well, which refers to a biological learning approach, the idea where the computational models are designed to emulate what happens in a biological brain, human or otherwise. Generally, neural networks are not designed to be realistic models of biological brains. So why use neural networks at all? There are two motivations presented. The first is that real brains provide proof that a brain-like system can create intelligent behavior. So the idea is that intelligent behavior could be created by emulating real brains in a computer. Another notion is that the process of building such networks might shed light on how brains work, which could provide much value in and of itself, aside from the technology's applications. Quote, "The modern term deep learning goes beyond the neuroscientific perspective. It appeals to a more general principle of learning multiple levels of composition, which can be applied in machine learning frameworks that are not necessarily neurally inspired." End quote, from page 14. Linear models such as this were the first stepping stones to modern deep learning. The idea was that the weight factors assigned to inputs could be tuned to optimize the output. In this context, the tuning refers to a primitive type of learning, where the weights could be determined with enough sample reference data. The algorithm used to solve that problem, which was, given these inputs and these outputs, what are the weights, was a special case of the stochastic gradient descent. Modified versions of that algorithm remain the dominant training algorithms for deep learning models today. Linear models such as these are still some of the most widely used, though often they are trained in different ways than they were before. It should be noted that linear models have many limitations. One famous flaw was the inability to learn the exclusive OR function. The exclusive OR function is presented here on this slide. The inputs are simply not possible you can't achieve this function basically just having one discrete set of weights. It's this kind of different computation. This simple algebra of just multiplying inputs by weights to achieve an output, it cannot yield this exclusive OR function, which is like more of a logical function. Following from this discussion of historical beginnings, it should be noted that the brain is no longer the main, most prominent guide for the field of deep learning. The reason for this is that today the brain still holds too many secrets. We don't know enough about how it works, and we're far from understanding even the most simple and well-studied parts of the brain. So we can't use it as a further guide, step-by-step guide to constructing brain-like computers. One notable caveat to that last topic is that there are some evidence to suggest that a single deep learning algorithm can solve many different tasks. The example cited is an experiment where ferrets could, quote, learn to see with the auditory processing region of their brain, if their brains are rewired to send visual signals to that area. This suggests that much of the mammalian brain might use a single algorithm to solve most of the different tasks that the brain solves, end quote. While biological brains have inspired successful neural network architectures, there are too many unknowns as of yet with respect to brain functions for them to provide guidance for the design of the learning algorithms operating within those architectures. Deep learning should not be interpreted as an attempt to simulate the brain. The field of computational neuroscience encapsulates the endeavor to understand how the brain works algorithmically. As was seen in the previously presented chart, a component of the second wave of deep learning was the Connectionist movement. The principal idea was that, quote, a large number of simple computational units can achieve intelligent behavior when networked together, end quote. A key concept developed at this time is that of distributed representation. This can be explained as the distribution of the representation of an object's features among many neurons. One way to think of this is that neurons should be efficient in the sense of redundancy. There shouldn't be redundant neurons. There shouldn't be neurons that are triggering for the same features in combinations with other features. Rather, there should be individual neurons identifying individual features, which can then be grouped to create a multiplicity of features that an object represents. That represents an object, rather. Another corner of the Connectionist movement was the idea of backpropagation to train deep neural networks. At the time of writing, the backpropagation method is the dominant approach to training models. In the 90s, some fundamental problems were identified in the modeling of long sequences with neural networks. These problems were partially resolved with the LSTM, long short-term memory strategy. This is still widely used today. There was a downturn in neural network breakthroughs from the mid-90s to 2006. Part of the reason for that was that hardware made advances that made computational endeavors possible that weren't before. In 2006, quote, Geoffrey Hinton showed that a kind of neural network called a deep belief network could be efficiently trained using a strategy called greedy layer-wise pre-training, end quote. This will be described in more detail later in the book. It was then proven that the same strategy was applicable with different networks as well, and improved performance with respect to generalization on test samples. Generalization is the concept that a model works well generally, as opposed to specifically, a general model works well not only on the data with which it was trained, but also on the data which it has never seen before. Around this time, the term deep learning became popularized, as researchers were able to train deeper neural networks than they could before, and, quote, deep neural networks outperformed competing AI systems based on other machine learning technologies, as well as hand-designed codes and algorithms, end quote. It should be noted that the focus of exploration and research has changed much since the beginning of the third wave. At that time, research was focused on unsupervised learning and strong generalization from small data sets, where now there is much more interest in supervised learning algorithms and the use of large, labeled data sets. One of the things empowering the great advances made in the latest wave is the digitization of societies in recent years. The ubiquitousness of computers means so much more data is recorded than was in the past, and that availability of data is the keystone for successes with deep learning models. In fact, many models solving highly complex problems today are nearly identical to those that struggled to learn simple tasks in the 80s, because now they have such greater resources with which to learn. Quote, as of 2016, a rough rule of thumb is that a supervised deep learning algorithm will generally achieve acceptable performance with around 5,000 labeled examples per category, and will match or exceed human performance when trained with a dataset containing at least 10 million labeled examples. Working successfully with datasets smaller than this is an important research area, focusing in particular on how we can take advantage of large quantities of unlabeled examples with unsupervised or semi-supervised learning. End quote. In addition to data availability, the availability of hardware and computational power has driven great success in the field of machine learning. This includes the advent of different kinds of processing units and processing methods, such as distributed computing. Quote, larger networks are able to achieve higher accuracy on complex tasks. End quote. I recommend seeing the text for more information to accompany these figures. It's quite interesting to see how many neurons these systems have and how many these animals have. This figure shows the error rate of the winners of the ImageNet Large-Scale Visual Recognition Challenge. More details on the progression of the technology can be found in the text, but the gains that have been made are tremendously apparent and are getting better. In particular, deep convolutional nets consistently lead in the image recognition category. Another development is the application of neural networks to model relationships between, quote, sequences and other sequences rather than just fixed inputs, end quote. The concept of the RNN, which is applicable here, was new to me when making this presentation. I found a great video explaining it, so link to that in the description. Essentially, it seems that this kind of network takes in an input, creates an output, and that output is the input for the next iteration, or a component of the input. So in this way, the sequence in which data is inputted has an effect on the output, and this has significant applications in language processing, among other interests. Reinforcement learning is another area of great success. In this paradigm, the neural network determines the agent's actions, given rules governing a system within which it takes those actions. It learns how to operate and achieve some goal by trial and error, without guidance from a human operator. This kind of system has achieved human-level performance at tasks, such as DeepMind playing an Atari video game. Full disclosure, at this time, this is the field I'm most interested in, and I might be biased in paying more attention to it in this project, working through the book. Advances in deep learning depend heavily on developments in software infrastructure. You'll need to work with these to effectively implement machine learning methods. So FYI, the authors refer to the following software libraries: Theano, PyLearn2, Torch, Disbelief, Caffe, MXNet, and TensorFlow. So that's the end of my presentation for Chapter 1. Again, this is a learning process, my process of creating these presentations and working through this project. So, open to feedback, and I hope that this might provide value. Thanks for watching. Take care.